Hi everyone, this is Alyssa, your TA here, and I am here with your second demo. Mostly we are going to be talking about networks, real data, and how to do measurements on those networks to learn some information about the data set or whatever model we're looking at. So I thought it'd be nice and easy to start with our friendly neighborhood cellular automata. And the reason why I like to start there is because, as you guys know, it's fun to think about the world in terms of zeros and ones, as my favorite thing to do. But it's also really great to think about it in terms of states of the world. Like you look at the room around you, and it's in a particular state, it's in a particular configuration. And it's nice to think about transitions between those states. So let's explore this a little bit more explicitly through networks. So, for example, one question we would want to know is all the possible states that the universe could be in. We might want to know all the possible transitions between those states, right? So, like, how can we get from one state to another state? Well, we can do that with a cellular automata extremely easily. So let's pretend we are starting with a cellular automata of a width of 3, right? So we have a universe that is 3 bits big, and every bit can be either a 1 or a 0. And we want to know what all those possible states can be, right? So from before, you know that there are 2 to the 3 possible states, because there's a 1 or a 0, that's just 2 of them, and then there's 3 cells big. So you've got all your possible initial states, and you can calculate it in Mathematica with tuples, right? So what tuples does is it basically generates a list of all possible n tuples of elements from your list that you give it. So we give it a list of 0 and 1, because that's what we want it to choose from. And we want it to choose things, all possible things that are size 3. So there you go, you get 8 possibilities there. Alright, so now what we want to do is run all these states in a cellular automata of time step of 1, right? So we can do that in a table, so that's basically just a loop. The format of the table looks like this. So you give it your function like that, and then you give it your variable in your function, and then you can start it from 0 to something or something to something, and in increments or whatever. But we just want it to go from our initial condition is our variable, and we want it to choose from this list. So we want it to go through this list of initial conditions here. So we don't have to visualize these CAs because we're not interested in looking at them. We're interested in looking at the network that it creates. So while we're at it, let's go ahead and see what these transitions look like under all the possible rules, not just rule 0, because rule 0 is boring, right? It always just goes to all zeros. So what we can do is we can modify our table here, and we can do a double loop. So can take in more than one variable, right? Because here our variable is our initial condition, but we can also have an initial condition and a rule. So it does a double loop. So if we set it up this way, where we have our initial conditions on the outside and our rules on the inside, what we get is we get a result that looks like this. So let's go ahead and show all, just so you guys can see the structure of this sort of thing. So this is a lot of curly brackets, right? It's a little bit difficult to deconstruct here. But what you can see is this is a chunk of initial conditions, and this represents one rule over all these possible initial conditions, right? So it's always important to understand what your data structure is when you're trying to visualize things or processing data. Alright, so like I said, we don't need to visualize these things, right? But what we want to do is we want to see it on a graph. And we can do that by simply saying rule, and then this nice little triple @ symbol here is another mathematical shortcut for apply this thing to the first results, right? And the first results, since this is our giant results table, it's huge, right? Let's just check our first one, which is rule 0, because that was the first rule we looped over. And it just looks like this, right? So if we do rule triple @ symbol, we get these arrows between these things because there's a bracket around these two states. So this is time step 1, time step 2. So 0, 0, 0 always gives us 0, 0, 0 for this rule. So pretty cool, huh? And if we have it set up this way, it's really nice because in Mathematica, we can just feed that straight into this graph function, and it's going to read this as an edge list And then we can just add some other options here, like vertex labels, where we give it the name. So we can label our vertices in terms of what the state is. And then we can give the plot a label, which is 0, because this is rule 0. And it matches our intuition and everything we know about rule 0, right? So all of our states go straight to rule 0. So yay, we have networks, exciting. So we didn't even need to visualize this, especially if you're doing large data sets. You might not even need to visualize it. You might just want to go ahead and do straight measures on it, which we will do. So say you want to get really fancy, right? So this was all really cool and everything, but what if I want to see all these networks for every rule? Like I want to visualize this whole table, right? All this results. This is all of our data. So if I wanted to visualize all of our data, I'm going to have to figure out a clever way of looping through all this data in order to make a lot of visualizations. So like a table of visualizations, right? So we would have to actually make something, what we can do is we can make something nice and fancy. So in Mathematica, we can make special functions. So like built-in functions like cellular automata, table, tuples, things like that, we can make our own. So this is the structure and how you do it. You call it something. So we're going to be really boring and call it f. Sorry. But it can take in as many variables as you want it to. We're going to have 2 variables. So the first variable is going to be x, which is a part of the data, and then r, which is a rule, what rule it corresponds to. And we're going to want that rule because we want to label our network or our graph. So our special function is going to take in 2 different functions. It's going to take in graph and rule. So this is the thing that we used earlier. So we're going to take rule and apply it to that part of the data that we want. And we're going to make a graph of it, right? So we have vertex labels, which is our name, which is just it's going to be the states here. And our plot label is what's going to be our rule, because we want it to be like this up here, where we said plot label is 0. And then image size is medium, because we don't want it to be too tiny. You can make it large. You can also make it full size. So now what we want to do is we want to take our function and we want to loop over it. So we put it in another table, surprise, surprise, my favorite thing to do, and we say f, where our first variable is results, which is the rule plus 1. We'll get back to that in a second. And then the second one is our rule. So if we start at rule 0, because we're going from rule 0 to 255, this one's intuitive because it's just a rule, but rule plus 1 is necessary because Mathematica enumerates things starting from 1, whereas in Python it starts things from 0. So if you're starting at the zeroth element in your list, then you're starting at the first one. But Mathematica actually starts with 1, meaning you're at the first one. So if you're at rule 0, you need to add a plus 1 there. All right, and then we can run it, which I already pre-ran, takes a second, so I cheated. And we get all of our pretty plots here. So you get them in a nice sort of like table function, but you can click them to highlight to see which ones belong to, because sometimes it's a little bit tricky, right? Because you have a lot of disconnected components to your graph. Like for example, here you've got a lot of little islands that your network is stuck on. Some of them you have an entire component. It's a fully connected graph, and you don't have to worry about that. But you can actually see how easy it is to tell what states are the absorbing states, right? So like all zeros, it doesn't matter where you start from. You're always going to end up in all zeros no matter what happens. But if here, like for example, rule 13, there are many sort of absorbing states, which is really interesting. So you can start from anything here, and you end up like in a universe of only 1 1 and 2 zeros. But if you end up here, all ones, or you go to all zeros, and vice versa. So it's a fun way to look at data.